Yes. Hello all and welcome back to the workshop of self-healing. And the next presenter will be Maria Wilkman, who is a principal scientist at Research Center here in Finland from VTT. And she is also the coordinator of Hidden project that is under the battery2030 plus, and the title of her presentation is self-healing functionalities for metal lithium batteries. So floor is yours, Maria.
Thank you, Mari. Nice to be here. So I will share my slides here. And I believe you should now see them. And then the pointer, yes, okay. Great, so let's start. Welcome indeed also on my behalf. And today I will talk about self-healing functionalities for lithium metal batteries. And I come from VTT, as mentioned by Mari, and I'm coordinating the Hidden projects where we are developing such functionalities. But today I will also try to give like an overview of different methods how we can increase the lifetime of lithium metal batteries. Okay, so I will first start the presentation by a short introduction to lithium metal batteries, and hopefully we'll be able to explain how they differ from the more conventional lithium-ion batteries and what are the main challenges and benefits of them. Then I will introduce a few methods which are like general methods to increase the lifetime of lithium metal batteries, and then give you a few examples how we can prevent the aging of lithium metal batteries, and then how we can even cure some problems that may arise in such batteries. And then in the end, I will give a short introduction to the Hidden project and explain what we are doing there to increase the lifetime of the batteries, and then a few conclusions. So to start with lithium metal batteries. So they are batteries where we are replacing the graphite or silicon anode with a metallic lithium layer. And the main benefit in this approach is that we can, of course, increase the energy density of the battery when we have a very dense metallic anode instead of the porous graphite anode, for example. And this helps to make smaller batteries, which will then enable, for example, increased driving range for electric vehicles, which is, of course, very much looked for. But lithium metal batteries still have some challenges. So mainly there are still some issues with the lifetime, and there are several reasons for these problems. So one of the reasons for the low lifetime is the so-called dendrites. So dendrites are metallic lithium wires growing from the anode during cycling. And if they grow too long, they can reach the cathode side, and this will cause a short circuit in the cell. And also, we might have problems with inactive lithium, so-called dead lithium, which is also formed during cycling. This causes like a loss of the active material. Since it's an isolated lithium particle, it's not active in the battery anymore, and that leads to issues as well. And then especially if we are using solid electrolyte, there can be some voids or like empty spaces forming between the anode and the electrolyte. The contact, electrical and mechanical contact, might be lost during cycling. since there are some volume changes in the cell. So this is also a problem that still needs some attention. So these are all related to the lifetime of the battery, but then of course we still, in addition, need to think about other things when trying to commercialize these such batteries. So manufacturability and cell assembly need to be a bit modified compared to the lithium-ion batteries with the liquid electrolyte. Also, the solid electrolyte needs some attention still. We should still aim for higher ionic conductivity for the electrolytes. And then recyclability of the lithium metal batteries needs to be also thought of, since even though the cathode might be the same than in a lithium-ion battery, the metallic lithium anode will require some changes also in the recycling process. But today I will focus only on this lifetime issue, and then the others are then a topic of a different workshop. Okay, then the electrolytes. So in a lithium metal battery, we can use different electrolytes. So it's even possible to have a liquid electrolyte. Then there are a lot of examples of polymeric, organic polymer or gel electrolytes, which are still somehow soft, but not anymore liquid. And then there are inorganic solid state electrolytes, which are much more rigid, and for example, oxide or sulfides. And in principle, the harder the electrolyte, we can increase the mechanical strength, which will then prevent the growth of dendrites. But in real life, it's not that simple, since even these very hard ceramic inorganic electrolytes or cells with those suffer from dendrites. And the reason is that we would need to have a perfectly homogeneous single crystal of the inorganic electrolyte in order to avoid dendrites, since there are always some grain boundaries and crack formation, which will then eventually cause the dendrites to grow in those like areas. But there are methods, either self-healing methods or other protective methods, to increase the stability of the cell for each of these electrolyte types, and the methods vary depending on the type of the electrolyte. So I will still, before going into more details regarding the different methods, give a short introduction to the history of lithium metal batteries. So this is actually quite old cell type, and the first rechargeable lithium metal batteries were demonstrated already in the 1970s, and they were sold commercially in 1980s. But soon it was noticed that the metallic lithium reacts with the liquid electrolyte quite aggressively, and that led to safety problems with the cells. So it was mandatory to recall the cells from the market, and also the research bit slowed down for more than 2 decades, and it was focusing more on the lithium-ion batteries with a graphite anode, since they were more safe than these ones. But now, due to the very high demand for high energy density batteries, especially for electric vehicles, but maybe even for like electric trucks or even planes, who knows in the future, there is a high demand for high energy density. So that's why the lithium batteries have become again more attractive. And during the past 10 or 15 years, there has been a lot of activities again, both in the industry and academia, regarding the lithium metal batteries. Okay, and then Roberto Domingo already gave you an introduction to the kind of self-healing in general, but I still summarize here a bit the idea of self-healing. So the self-healing methods can be divided in several different ways. This is one way of dividing them in 2 different groups. So they can be like called preventive or autonomous methods, or then curative. So on the left-hand side, here is an example of a preventive self-healing method. So it's like if you eat healthy and exercise, then you most likely will have a longer lifetime. So this is, you can think the same for the batteries. So if there are some methods to slow down the degradation, we can increase the lifetime of the batteries. This is more simple way, but then in some cases, it's not possible to find this kind of preventive ways to increase the lifetime. Even though you would eat healthy, you might get some kind of a disease. So same applies for batteries. So sometimes there is a problem which we were not able to prevent. So then we will need some curative ways to heal the battery. And that requires triggering. So we need to, first of all, know that something is going wrong. We will detect a problem. Then we will trigger the self-healing method with some either mechanical improvement of the cracks in the battery, or then some chemical treatment like pills here. And then we will achieve the recovered performance for the cell. So these are a bit different, but anyway belong under the same family. And I also put here the recycling symbol, since we might even consider recycling of the battery to be a curative self-healing method. I know it's not kind of defined so, but then we will kind of take the battery parts from the cell, and for example, with direct recycling, we might be able to heal some layers of the battery and then reuse them. So that might be even considered like an extreme case of self-healing. Okay, so first here are some like general examples how we could increase the lifetime of the lithium metal battery. So there are several ways presented in literature, and I have just added here a few, and I have listed some references still on the slide, so you can check more details from them. But there are different ways to increase the lifetime. So we can focus on the metallic lithium anode. So there can be different lithium alloys. We can optimize also the lattice structure of the copper current collector. Have some 3D structures in the anode or lithophilic layers, and these all help to have like a smooth lithium nucleation on the anode, which will prevent the growth of dendrites. Then there can be also like an artificial solid electrolyte interface between the lithium anode and the electrolyte, or a barrier layer. This will help to stabilize the lithium electrode. Also, we can have an electrolyte called single ion electrolyte. So normally both the anion and cation are moving in the electrolyte, but if we have like a polymer electrolyte where only the cation can move and the anion is bonded to the polymer backbone, so that will also help. Or if we just can somehow increase the lithium transference number, that will also help to prevent the dendrite growth. Since if the both anions can move, then during cycling there will be an electric field forming at the electrolyte and lithium interface, which will again accelerate the dendrite growth. So this is one method to slow down slow down the growth if we can have just like a single ion electrolyte. A bit the same is with the liquid crystal electrolyte. So liquid crystals are materials that are between solid and liquid, but they are structured, so they can control the flow of the lithium ions inside the cell. So if lithium ions can move only in one direction and not across the anode surface, that will also control the flow of the ions, which will help to have a homogeneous lithium growth during cycling. And then we can, of course, increase the pressure in the cell. That will especially help with the contact loss at the interface. But there is, of course, a practical limitation. We cannot increase the pressure too much, then it's not anymore possible to like use those cells in a real battery pack. So these are kind of like, I don't know, could they be called like passive methods to increase the lifetime? But self-healing, in my view at least, means that the materials that we are, or the methods we are using, are somehow stimuli responsive. So something happens and then the materials will adapt or have some function afterwards. So are there such methods to increase the lithium metal battery lifetime? And yes, so we start to have also this kind of self-healing stimuli responsive materials available. And first here, a few words about the preventive or autonomous ways to increase the lifetime with self-healing methods. So here we have an example of a barrier layer. So this is the copper current collector, then the lithium metal anode, and then we could have here like an artificial say layer on the lithium metal, which will protect the metal from reactions with the electrolyte. But then when we charge and discharge a battery, there will be quite heavy volume changes in the lithium metal. So it can be, the thickness can increase by 15 microns or even more during cycling. And it will shrink and expand continuously. So then you can imagine that if we have a rigid barrier layer on top of the lithium metal, it might break during the cycling, and the lithium ions need to go through this barrier layer. So there might be then again cracks forming into the barrier layer, and these cracks then are the places for the dendrites again to grow. So it's not a perfect solution. But then if this barrier layer has some self-healing properties, then it can adapt to the volume changes that we see happening in the lithium metal anode. And here I listed 3 examples of self-healing say layers. So as mentioned by Robert, some metal alloys can adapt to the volume changes. So they are close to liquid form at lowest temperatures. So they can like flow during the volume changes, and it helps to have a flexible barrier layer on top of the lithium metal. Then there have been examples using lithium-rich antiperovskites as the barrier layer. So they have very high ionic conductivity, and even though it would crack, the lithiums would like to flow through this very highly conducting layer and not from the cracks. And then there will be a new barrier layer forming on the crack, and then it will kind of glue these antiperovskite parts together during cycling. So it has some self-healing properties as well. Or then we can use like a polymeric barrier layer. For example, these uridopyrimidine groups have dynamic hydrogen bonds. So if they will shrink and expand, the dynamic hydrogen bonds can again bond together after the volume changes. So this is an example of a self-healing layer as well. And again, one method for this kind of preventive self-healing is a piezoelectric separator. So piezoelectric materials in general are materials which will generate the voltage when they are deformed or bended. And it is possible to make a porous piezoelectric film, which can then act as a separator in the battery. So then you can imagine when dendrite is growing, it will hit the separator layer and it will bend a bit. So then exactly on top of the dendrite, there will be a local electric field, which will then guide the flow of lithium ions so that they won't deposit on the dendrite, but in between them. And here is one example of a piezoelectric material, PVDF. Polyvinylene fluoride is one of the materials we can use in this kind of separators. And then we can have preventive self-healing with functional electrolytes. So the first two examples are materials that can self-heal if there are some cracks in the electrolyte. And of course, these cracks are the place where the dendrites want to grow. So one is a polymer electrolyte. There are also other examples, but I took out these two here. So one is a copolymer, which has different blocks in the backbone. So one is to dissolve the lithium salts, then one side is for dynamic hydrogen bonding, and then still there are physical cross-linkers to increase the mechanical strength. So when there are some volume changes, this kind of material will be able to cure those cracks in the electrolyte. And then similar polymers can be used together with the glassy solid electrolyte, so ceramic solid electrolyte. If there are some cracks forming, this self-healing polymer can fill in those cracks in the ceramic electrolyte, which will help to increase the lifetime. And also we can have additives in the electrolytes. For example, cations with high reduction potential. So I tried to draw it here. So they will land on the dendrite, but they do not reduce into metals since due to the high reduction potential. So when lithium is coming here, this tip of the dendrite is already occupied with the positive ions. So then the lithium is forced to land between the dendrites, and this will also help to increase the lifetime. And but yes, then to the curative method. So there are not many curative methods yet for lithium metal batteries, at least as far as I know, based from literature. So they are still quite rare, but some have been presented. So this is one famous paper in Nature 2 years ago. So they used this so-called pulsed charges to reactivate the isolated dead lithium particles in the cell. So they had a hypothesis that, this is a direct quote from the paper, so that the short, fast lithium stripping step after the lithium deposition may promote the recovery of the isolated lithium and extend the longevity of the lithium anode. And they tested the method in lithium NMC coin cells. By a 2-minute activation, they were able to increase the lifetime from 30 cycles to 40 cycles. So this looks promising. And we actually tested this a bit in the hidden project in a real bigger pouch shell. But I can say it was not that simple to upscale this method in the higher scale, since the cells where we used activation actually degraded faster than the reference cell without any activation. And we think it was due to the consumption of the electrolyte. So this kind of method seemed to consume the electrolyte. So if we have a big pouch shell, we might need to adapt this method further. But it was anyway this is anyway a really promising method to increase the lifetime, but it still needs some work to be able to upscale it into bigger batteries. And here's the list of references, and you can check them here. And then I will still give a few examples of the hidden project that we are now working with. I believe I still have a few minutes time. And so the hidden project started 2.5 years ago. And this is our consortium, and it indeed belongs under the battery2030 Plus initiative. We are coordinating the project from VTT, and then we have partners from these organizations. So CNRS and University Grenoble Alpes from France are working with the materials and characterization. Then we have CSCM from Switzerland, who is, for example, developing non-invasive methods to detect the dendrite growth, and they are working with the battery management systems. Then we have Belenos, a battery producer, who is helping us to upscale the processes. And Berner Fachhochschule, again from Switzerland, as well as Belenos, and they are working with the lithium metal cell pouch shell assembly, and for example, laser cutting of the lithium metal anode. Specific Polymers is our material provider from France. They are synthesizing us novel electrolyte materials. And then Talos from Cyprus is our dissemination and exploitation manager. So the objectives in the hidden project are that we are indeed trying to prevent the dendrite growth in the lithium metal batteries. And we have two main methods here. So first one is a thermotropic ionic liquid crystal, and the second one is the piezoelectric separator. And so our goal is that we can demonstrate both autonomous and on-demand repeatable self-healing functionalities, which can be eventually even controlled from the BMS. And then the last point here is that we are also creating an industrial scale process for the self-healing batteries. So here is, for example, a picture of the roll-to-roll coating lines of VTT. So we are going into pilot scale and building pouch shell prototypes from the self-healing materials. And this is the first method that we have, so the liquid crystals. And so you can imagine when you have a liquid crystal electrolyte, it will already help to guide the lithium ions to flow smoothly or deposit smoothly on the lithium metal anode. It has been also shown in literature and by modeling by other groups than us that just having the liquid crystal as the electrolyte will already help to increase the lifetime. But anyway, eventually the dendrites might grow. So in this project, we are also trying to develop a curative method. So if there was some dendrite forming, we will heat the cell above the phase transition temperature of the liquid crystal, which might help to break the dendrites if there are any formed, or if there are any voids or loss of contact at the interface. Heating of the electrolyte above the melting temperature will help to refresh the interface. And we have developed a printed heating element on the pouch shell, which we can use at cell level to heat the cell above the melting temperature of the liquid crystal when needed, not continuously, but only like on demand. And then, of course, the electrolyte is a bit not so normal material to work with. So we had to also develop a processing method for that. So we are now using a method called melt infiltration. So we are coating the liquid crystal electrolyte on the cathode, and then we heat the electrolyte above the phase transition temperature. So then it will be infiltrated into the NMC cathode material. So here you can see an electrolyte layer on top of the NMC, and then some of the material will also penetrate the pores in the cathode. And this we already tested in pilot scale, this type of a method. And the second method we have is the piezoelectric separator. So here, as mentioned, when the piezoelectric separator bends, it will form a local electric field, which will then hinder the dendrite growth. And this is also something that we have upscaled in the pilot scale. So this is a roll-to-roll processed PVDF separator, which was first planned at CSEM and then upscaled at VTT into pilot scale. The cycling tests for this material are now ongoing, so I'm not able to show you the final results yet, but it so far looks promising. Okay, so just as a conclusion, so lithium metal batteries are prone to dendrite growth. Solid electrolytes cannot fix everything, so we need to have also some other methods, and self-healing methods are a very good option to help with these problems. Also, loss of contact at the interfaces is a problem still, especially with very hard ceramic electrolytes. So many kind of passive methods have been presented in literature. They are very good and needed, but in some cases they are not enough. So self-healing methods will help to improve still these passive methods further, so we can further increase the lifetime of the batteries. Most of the methods have so far tested only in lab scale, so it will require a lot of work to upscale everything. But anyway, I believe that self-healing has high potential to help with the lifetime problems. And here are still some websites or social media channels you can check to follow the progress in the hidden project. Our LinkedIn page, and then the website, and then my personal blog, where I try also to introduce battery topics outside the self-healing field in a simple way. Okay, great, thank you. This was all, and I will stop sharing. So if you have any questions, I'm happy to answer.
Thank you, Maria. So you can send your questions to the Q&A sections, and there are already some questions. First question is about the possibility to collaborate with Hidden Project.
Yes, it's very nice if people want to collaborate with us. So the project is still running for 1 year, and we would be very happy to collaborate with other people or project or organizations. So you can just like send me an email, and I will be happy to search for collaboration opportunities. This is one part of the whole initiative, that we should also link with other projects and not just work alone.
Then the second question is about the metal alloy. Is there any example on that an alloy or a metal has self-healing effect?
Yes, so I have not been personally working with these topics, but based on literature, there are some methods tested in small cells. So like an alloy of metal, which has a low melting temperature, which was deposited on the lithium metal, so that can adapt to the volume changes and have a self-healing, like a barrier layer between the electrolyte and the lithium metal. So at least in literature, such methods have been presented.
Then about the PVDF separator, does the PVDF separator then require NMP as a solvent? If so, are there any aqueous alternatives for piezoelectric separators?
Yes, so maybe Mari, you have better answer for that, but at least in the roll-to-roll process, we are using a bath where we remove some part of the material to make the structure porous. So there we are using a water-based bath. So at least there we don't have to use NMP. But Mari, do you remember what was the solvent in the actual coating?
DMSO.
DMSO.
Also and DMF.
Yes, so at least the PVDF material that we are using doesn't require NMP.
Then thank you for the nice presentation. The liquid crystal, it seems interesting for the dendrites to be broken. Do you have information on the integrity of the heated separator after dendrites are supposedly broken?
Yes, so we have not yet so far combined these methods, so they are different. So we don't heat the cell with the piezoelectric separator, and actually most likely it would not survive the high temperature that we still need for the liquid crystals. But in case, first of all, if we still need to work a bit to get a lower temperature to break or to melt the liquid crystal. If we can get the lower temperature, then we might be able in future to combine these two methods, but so far they are separate. So indeed, a good question.
Yeah, related to the temperature, what is the temperature that you are mentioning?
Yes, so we are now using a model liquid crystal electrolyte, which requires still a relatively high temperature. So above 100, even up to 120 degrees. So we consider that still to be a bit too high for the cell, even though we have tested that the cell structure, like the casing, still survives such high temperature, but it would not be very practical in real life. So we are now trying to use, for example, modeling to develop materials that would have lower melting temperature, hopefully closer to 60 degrees than 100 degrees, but this is still something we are working with.
Then more about the separator. What is the specific role of piezoelectric separator? Is there any self-charging effect of the separator?
Yes, well, the piezoelectric separator will just work if there are dendrites hitting the separator, and it will bend. So this local electric field will then guide the lithium ions to travel into the direction where there are no dendrites. So this is the main mechanism in the cell. Self-charging, I'm not sure. Do I have an answer for this? Probably not for this question. I don't know. We haven't tested at least.
Then about the liquid crystal itself, very interesting approach for the melting infiltration of liquid crystalline electrolyte on the NMC cathode. What size of batteries has this been scaled up for? Means in the ampere hour.
Yes, so the size, like the physical size of the batteries, is around 5 years for the pouch, and so far we have been making single layer cells, so it's not yet assembled in multi-layer structures. Ampere hour, I don't now remember the exact number we have, but I can say that we still would need to increase the conductivity of the liquid crystal electrolyte to have perfectly working cells. So it is not yet a ready process, but the melting filtration indeed seems to work. But then the liquid crystal properties need to be still tuned to make a better working battery with higher ionic conductivity.
Thank you. We still have time for more questions. And the second one is, the next one is, what is your comment on the ALD technique to reduce dendrite formation?
Yeah, ALD is a very promising method, and we are using that also ourselves in some other projects than in Hidden. And it can indeed help to prepare a barrier layer on top of lithium metal. And it will increase, as a passive material, the lifetime of the battery. Usually the materials are like maybe not so flexible, so they are rigid materials. So ALD, well, I don't know, but it might still have challenges when there are volume changes in the lithium metal. So if it will crack during cycling, the barrier layer made by ALD, then it might not be a perfect solution yet. So if we can combine ALD with like some kind of flexible material, which will help to cope with the volume change, then it would be still a better solution. But ALD as such already helps with the lifetime, and especially on the cathode side, not dependent on the type of the anode we are using. So I would see much more potential on the cathode side if we coat for example, the NMC layer with ALD. There it is very beneficial to use this type of coatings. But with the lithium metal, still maybe some kind of adaptive self-healing material would be better.
Okay, then you were talking in the beginning about these electrolytes, 3 different types of electrolytes. And what is your own opinion about those? That what would be the best electrolyte with the lithium metal?
Yeah, I'm a polymer chemist or physicist by training, so maybe I have a bit biased opinions, but I like polymers. But liquid electrolyte might be a bit challenging, even though there are some methods to help with the lifetime. But maybe I would say that I would, at least in the near future, the polymer electrolyte looks to be most promising, but there we still need to work with, for example, the ionic conductivity. So probably a combination of polymer electrolyte and inorganic electrolyte might be the best solution. Since you could combine the soft properties of the polymer to cope with the volume changes and self-healing, maybe even with some dynamic hydrogen bonds, and then have the with more mechanical strength and higher conductivity from the inorganic electrolyte. So this type of a hybrid approach would be my favorite, I would say.
Okay, well, we still have time, but maybe we will go further. What do you say, Silvia?
Yes, thank you very much, Maria. We get a lot of questions and also very, very interesting presentation. So if Rita is available, we can start immediately with the last, let me say, talk of today. So first of all, I want really to thank Rita to help us in this important presentation on the modeling aspects. Modeling aspects are, as in all topics now, becoming more and more important in all fields. So Rita Magri is working in the University of Modena, Reggio Emilia in Italy. She's participating in Bat Forever project. So also one of the two projects together with the hidden project presented by Maria in the field of self-healing under Battery 2030 umbrella. Rita has a wide expertise in the field of modeling, starting from atomistic model and so on. And so she will drive us in this new environment compared to the more experimental one we saw all together, giving the basis on this. And so thank you very much for accepting. And the floor is yours. I hope you can share your screen.
Yes, I hope so. Can you see it?
Not yet. We can see you now.
Okay. Share
You have to click
screen.
on the share screen, yes, and then define what do you want to share. Okay, now is start arriving. Perfect. We see your screen. So if you can go in the presentation mode, it's perfect. Thank you very much, Rita. The floor is yours.
Okay, thank you, Silvia, for your nice presentation of me and my work. And yes, I had a late notice to prepare this talk, so I hope it will be, however, very useful. And so my name is, as you already know, is Rita Magri, and I work at the University of Modena in Reggio Emilia. And I am part, a beneficiary of the Bat Forever project inside the Battery 2030 Plus collaboration. And I will talk about how to model self-healing functionality for battery components. In the Bat Forever project, we will address autonomous self-healing through the synthesis and study of polymeric materials for binders and electrolytes. And so for going to the next slide. Okay. So in this talk, I will focus more on the binders. And binders are multifunctional material, and they have many requirements. They must hold electroactive materials together, improving the mechanical and chemical stability. So they have to have good adhesion to the active material surfaces and also to the current collectors. They also are required to have a good electronic and ionic conductivity. And also, since they have to allow for volume changes under lithiation and delithiations, they also need to have reversible elasticity. And also we want them to have also self-repairing functionality so that they can repair themselves when they are broken or when the active materials got cracked. Obviously, the modeling of the binding materials has to consider all these issues. So is a very challenging job to try to model these kind of materials because of these many requirements. So we have many aspects that need to be simulated and taken into account together. Okay, what we are studying in Bat Forever. so self-healing electrodes. In particular, we are interested in silicon anodes. Silicon is a challenging material for anodes because it undergoes a 300% volume changes under charging and discharging, so a continuous volume expansion and contractions that induce in the material surface cracks and eventually the pulverization of the entire particle. So the anodes, as shown in the picture, has a role to keep the particle together and to allow for the volume expansion and contraction, and also to heal the surface cracks when they form. On the other side, for the cathodes, we propose NMC core shell particles, and also cathodes have problems, and so we study the protection of the cathode surface through self-healing binders. In the case of the cathodes, is necessary to stabilize the surface, inhibiting transition metal and oxygen losses, and any chemical reaction that can modify the surface and lead to loss of material. Also, it's very important for the binder to have a good interaction with the electrolytes and a good role in the CI formation. Okay, so now I start to talk about some computational techniques used to model materials and asking this question. So how we can model or simulate these complex systems. So multi-scale approaches have been proposed in the last decades, and there are many ways to apply multi-scale concepts. So the main idea is based on the fact that we have many, let's say, computational techniques, but each technique is good only for a narrow time and length scale. So, for example, we can focus on this cloud-like plot. So at in the time range of from the femtosecond to the picoseconds and length scale from the angstrom to few nanometers, we have this called ab initio methods, which are very accurate, but you can use them to describe only at most very few hundreds of atoms. So systems of very small dimensions. For larger scale, length and time scale, we have to resort to different methods, like classical molecular dynamics or semi-empirical methods, which can treat, again, still atomistically, but they can treat thousands of atoms, system with thousands of atoms. And then if we want to address problems or processes occurring on time and length scales, longer time and length scales, so we need to resort to other methods like statistical methods, like here, the kinetic Monte Carlo method, and eventually to the continuum equations like the finite element methods on which the multi-physics packages that probably you know are based, which can simulate the system on scales which are directly comparable with experiments. Okay, this other plot shows an alternative idea of a multi-scale approach. In this case, here we have the shorter scale, smaller scales, in which the basic unit for the description is just the atom. And then we describe the interactions between atoms at this scale. Then to form this interaction, to form molecules in small clusters. Then on a larger scales, you can take as a basic unit of the theoretical description, the small clusters or the molecules, and then to describe theoretically or simulate larger clusters. Then you can use as a basic unit for the description, the larger cluster, to describe more complex aggregates, and so on. And then the interface of these aggregates with surfaces to analyze interface, and so on, growing always more and more complex systems until you arrive to the description of the entire cell. So the idea is we start from the small, what is small on the atomic scale, and then we grow on, we proceed on longer time and length scale until we reach scales that are directly compatible with experiments. But this is a very nice, appealing idea. But the challenge, as is written here, is just how to link this method. Okay, how we can, what we have to calculate inside each method, and then to pass further to the other methods. So what are the quantity and what parameters, how we can pass these parameters that will enter, for example, kinetic Monte Carlo or the continuum equation. Okay, so this is the main idea. In this slide, I will introduce another concept, which is very important from a computational point of view, which is the calculation of energies. In particular, we want to calculate the so-called insertion or absorption or substitutional energies. And so we need a method to calculate the energy of a system, or a material system. And for example, the intercalation or insertion or absorption and so on energy is defined as the difference between the energy of the system with intercalated atom minus the energy of the perfect system without any atom intercalated, minus the energy of the single atoms taken from a proper reservoir. Okay, so but obviously this is the basis to address, for example, chemical potentials of lithium in the cathode and anode material, and to assess the calculation of the open circuit voltage, for example. But obviously we need a strategy to calculate in a very accurate way the energy of these energies. Since we want to calculate this energy, we need to describe chemical bonds and the electronic charge between atoms. So we need to resort to quantum mechanical methods. And the workhorse of this kind of calculations is a density functional theory that almost everybody knows. And in this method, which is atomistic, so each atom is singularly considered, also the electrons are treated fully quantum mechanically. And they are so described, as you see here, by the wave functions. And so we need to solve the Schrödinger equations for these electrons, and with an effective potential, which is a functional of the electron density. This is the reason density functional theory. So electron density nr, which is calculated from the electron wave functions. Okay, so and it is always said that this method, density functional theory, is an ab initio method. What does it mean? It means that no experimental data are given in input. So in practice, this method should be just only theoretical. So from ab initio. So to do it, we solve first using density functional theory the problem, the atomic problem, and we derive the potential felt by each electron in the atom and its wave function. Then when we have all these potentials felt by the electron in that atom, we superimpose the potential at each centering it at each ionic site. And so we build an entire potential, which is called in this case external potential, which is the effect of all the ionic cores on ions on the electrons, on all the electrons. And once we have solved this self-consistent problem, we are able to calculate for the total energy of the system. Okay, and while this is useful not only to calculate the intercalation energy and the open circuit voltages, but also to simulate, for example, lithium diffusion in silicon. In this slide, I show you a method which is called the nudged elastic band, which is usually implemented in the packages, in the code packages for ab initio calculations, in which we see the main idea. So we have the energy here, the scale, and the energy of initial state of our system, and then we have the final state and the energy of the final state of our system, which are usually lowest energy situation for the system. And then this method allows us to find the so-called minimum energy path. So that is a trajectory that the system would follow to start from the initial state to arrive to the final state. And at the top of this, there is a so-called transition state. This allows us to calculate the activation energies for the processes as a difference between the energy of the transition state and the energy of the initial state. So, which is the barrier in energy that the system has to overcome to finally arrive to the final situation. I have used this method also for studying chemical reaction catalyzed by some catalyzer, with studying the development from some reactants to some product and calculating the activation energy for the chemical process. But it can be used also to study silicon diffusion, as a lithium diffusion in silicon. For example, here are positions lithium, of the lithium atom inside the crystalline of amorphous silicon. And these are lowest energy positions, so stable positions for the lithium ions. So we want to know what barriers the lithium has to overcome to pass from one side to the next one, So we can, at the end, obtain a trajectory and all the barriers that, the energy barriers that need to be overcome if the lithium follows, for example, this particular trajectory. So we can compare different diffusion trajectory inside the material. Another use for this energy barrier is that these energy barriers or activation energies provide a rate of a process. So, and then we can use these rates in a statistical algorithm, which is the kinetic Monte Carlo, which allow to simulate the progress, the development of the system in time. Usually this algorithm is very simple, so one has to individuate the sites where processes can happen and associate to each process its own rate. Then random numbers are thrown out, and depending on between 0 and 1, each one of these segments is proportional to the rate, and then a particular process is selected. Then once it's selected, it can be implemented in our system. The time is incremented, and then we restart with again choosing other sites and other processes. So we have a simulation in time of the evolution of the system. Using this method, we have, for example, studied the diffusion of an atom on a surface. And we can see from these results that the diffusion of an atom on this particular surface is not isotropic, but develops along a well-defined directions mainly. So this is what you can do with calculating energy. So calculating activation energies and studying also diffusion of lithium atoms in the systems. Now I will continue with some example, but on taking this example from what we are doing in the But4Ever project. Here we used mainly density functional theory, so ab initio methods. We have studied the interaction of monomers of some binder proposed by our partners on silicon surfaces, and also some conformational studies of optimization of these monomers. And then we have used the monomers to simulate also some dynamics of these monomers at different temperatures and different conditions using classical molecular dynamics. So we are we have worked mostly in this, inside this cloud. So here we have the boron acid polyaniline monomer and polyvinyl acid monomer. And we want to study, they were proposed by our partners, and we want to study the adhesion properties on a silicon surfaces. I don't enter into the computational details. I have no time. I will leave that those for the question and answer section. So we have considered two surface orientations, and we can see here that the two monomers behave quite differently when in proximity of a silicon surfaces. Most of all, very surprisingly, just the presence of the molecules distort all the external layers of the silicon surface. The PVA tends to form chemical bonds with the silicon atoms, while the boronic acid dope polyaniline tends instead to rotates only, but the interaction is mainly electrostatic. Also, we have studied the interaction between these two molecules, and on this kind of orientation, we have seen that there is no much of an interaction between PVA and the boronic acid polyaniline. However, things change when the orientation silicon surface orientation changes. So again, PVA tends to form chemical bonds through the oxygen atom with the silicon. Also, the interaction of BOH PANI with the silicon is stronger than for the other orientation, with these boronic groups tending to face the surface. And also there is an interaction. So this orientation of silicon favor the interaction between the molecules, and which creates hydrogen bonds between the oxygen of PVA, which is bonded to the silicon, and the polyaniline, the boronic acid group in the dope polyaniline. And also we have seen, looking at the adsorption energy, that the co-adsorption of both monomers is favorable than the adsorption of the single molecules or two molecules of the same kind. So then we have also looked at what happens when we put lithium, and here something very curious happens on this kind of orientation. And what happened is that the hydrogen detaches from the oxygen atoms in the boronic acid group and in PVA, and tends to attach, to passivate the silicon atoms in the surface, which is a very, very strange behavior. Next, we have optimized through molecular dynamics this monomer, and we have built optimized the mixture of the self-healing binders plus ionic liquids and lithium salts. And now we want to study the interaction of all the ensemble with the surfaces. Then we have also studied, and I go quite quickly on that. We have studied conformational, different conformers of these monomers. This was what we obtained by our partners, a suggestion for the boronic acid dope polyaniline. We have optimized through DFT this structure. And then we have studied different conformers, changing the disposition, orientation of the rings, the position of the nitrogen atom with respect to the boronic acid group, and so on. And then we have found 14. They are have no imaginary frequencies, so they are stable and very close in energy. When we use them in the molecular dynamics run, we found a very strange that the bonds, OH bonds, are not staying like that, but they are preferred in this tilted geometry. We resubmitted this geometry to DFT and found that there actually is lowest energy configuration. So the bonds are tilted. Then we want to go from monomers to polymers. So we have implemented all these results in building larger structures. So we are now implementing the multi-scale approach in which we start from monomers and then we optimize it, and then polymers, and then we want also proceed cross-linking them with PVA and then study this in diffusion in the binder. Few words and then I close on classical molecular dynamics. This is used to study systems with thousands of atoms. Here electrons are not described, but only the interaction between full atoms. And these interactions is given through force field parameters. They are fit to experiments or fit to DFT results, or in these recent times, this can be optimized through machine learning algorithms. And here, this is the potential used in classical molecular dynamics, in which we have a non-bonding part, so electrostatic and enertrons potential. And then we have some bonding parts of the potential to describe the energy contribution of bonds, of the angles, and the dihedral arrangements. And from this potential, we obtain the forces, and the system moves following a Newton classical dynamics. And again, we have done molecular dynamic simulations here for many systems, ionic liquids, and so on. But here I present results for the self-healing polymers. And again, boron, dopant, polyadenine, and PVA. And we have used different monomers, different conformance, and so on. And what the system has been fully optimized, and we have seen that the arrangement of the monomers is very interesting, and there is a clear formation of many hydrogen bonds between the monomers, in particular due to the boronic, here the boronic dopant of polyaniline and the PVA. So, and between boronic acid group between themselves and the polyvinyl alcohol. So, and so I think I stop here, and I thank you all for your attention.
Thank you very much, Rita, for the very interesting and complete presentation, very wide. So thank you very much. Is there any question from the audience? I start, and then I am sure that no one will be, people will not be shy enough. So these are very, very powerful methods to somehow to predict and to reduce number of experiments in the case of let me say, this kind of system, but for many other applications. So you are concentrating on binders as here. So do you, could it be possible also to predict in somehow, for sure, the performance of some binders compared to others, or also having some guidance for the choice of the best binder, also taking into consideration the environmental impact of them, or in somehow, so saying, okay, this has a good performance, I can show you where and which are the limitations, and finally if these can work so well that we have no environmental, the environmental issue is less important, or at the opposite, the environmental issue can affect the performance, but you can somehow change some of the components to reach enough good performance.
Yeah, yes, you can ultimately arrive to have good predictions from these methods. Obviously, I think in my presentation, I gave you an idea of the complexity of the problems, because to fully understand the behavior of the materials, you have to start to understand how atoms interact among them, and this is not an easy task, because it requires quantum mechanics, and these codes are very, very, very complex. But yes, so the main idea is just to arrive to make some predictions, and mostly to be able to explain also what is found in the experiments, because sometimes you can find some failures, or you can find some binders you use has not the performance you were expecting to, and but you cannot really understand why. So the power of these calculations is just that it can show what could be the main reason of such failures, because it can be in also many unexpected unexpected issues, that unexpected aspects of your material, of some characteristics that are not so easy to pinpoint, so to find out experimentally. And this so can give you some idea of why the performance you expected is not found. Is not
yes,
found.
This also reduces a lot costs on.
Well, on materials, yes, I think, but as I said, these are very complex calculations. Now they are trying to create some sort of algorithm that can collect results from all the different calculations that are made in many different groups to train some machine learning algorithm and some artificial intelligence, just because these calculations require lots of computational time, and they are long, so they require a long time. So it's not, they are not very routinely done, at least the so-called ab initio calculations. Obviously, the other methods are simpler. Depends on the complexity of the system there too. So kinetic, as idea, the kinetic Monte Carlo, or the solving system of rate equations, and so on. But yes, in this case, you need accurate parameters, and these parameters ultimately have to contain in itself all the information that you can collect from the atomistic calculation at the end. So I don't know if I answer your question.
Yes, sure.
So
now we have 3 questions in the Q&A. So
yeah,
the first one from Harish is, how does the OH orientations and the hydrogen bond interaction affect by addition on lithium salt? Which methods can be used to study the effect of salt? Maybe affect.
Yeah, no, we are actually studying it and creating this mixture of these binders that we have seen is forming dynamically during the simulation, these hydrogen bonds, and with lithium salt. So like pyrrolidinium, lithium pyrrolidinium, TFCI, so some anion to just study the effect of lithium in these binders. So we are collecting the results now to see how lithium can interact with these neutral binders. And then, as I shown in my slide before, we plan to study also lithium diffusion inside this binder and to check with the techniques that I've shown before. So to understand what trajectories, so if lithium binds with what atoms in the binders, or if the movement of these monomers or better polymers during the, for example, molecular dynamic simulation can help the movement of the lithium and to calculate its transference number. So we are now studying that.
Thank you. The second question from Brigitte. Brigitte is, thank you very much for the very interesting presentation. Regarding the force field parametrization, which will be more reliable to optimize FF parameter and DFT or experimental, considering the limitation of bots?
Yeah.
Very long question.
Yeah. Well, there are in literature already many parameters that have been optimized, both comparing with experiments and where they are available, because not always experimental data are accurate enough and appropriate enough to parameterize the force field. In many cases, in most of the cases, they are parameterized on the density functional theory, taking some molecules as example and working on the different geometries of these molecules. And so in such a way that these parameters then in the molecular dynamics run predict the DFT results. So for example, for the bonding energy, the angles between bonds energy, the contribution of bonds energy, and so on. Also, you need always to do some improving. When you start with a new system, you can, well, what we have done, we have taken parameters from the literature, but then we had to recalculate the charges, recalculate some other parameters to adapt to the problem at hand. So you use what is available, because the procedure to create a new force field for some system is very, as all the fitting procedure, they are very time consuming and heavy labor consuming. So
Thank
I
you.
don't know if I answered the questions, but.
So the last question by the moment is, can this technique, DFT and MD, be used to model electrolyte behavior under applied potential?
I don't understand well the
So
question.
while the cell is working, I guess. So if you are applying a potential, so while the cell is relaxing, working, could this technique, the FT, for example, used as, I guess, as to simulate the behavior, the model of the electrolyte during the cell working? Maybe this is the question. If
well,
who reported it can.
In principle, yes, more I see molecular dynamics more because density function, as I said, can only treat a small system, systems of small dimension. There are some form of molecular dynamics like the reactive force field, which are very promising to study, for example, real processes like lithiation in silicon or other reactive problems. So this is a newly proposed, but in this field, yes, there is always a technique that are continuously proposed and improved. Well, we can, so far I saw in literature that we can predict we can calculate some parameters of the cell, like the open circuit voltage, obviously capacity, studying lithiation in the electrodes with again multi-scale approaches, obviously. And yes, ultimately one can think is all a matter of time, computer time, and yeah, I think it's possible.
If there's no additional question, may I just ask you a comment? As there is a lot of discussion on the use of fair data, so the data you need and we all need to produce has to be somehow standardized in the form and so on. What is your comment on this? Because we are more experimental people and we have to help you at the opposite so that we can be helped by modeling people.
So we are doing some work together, the other partners, the partners of the other projects, to try to follow these fair rules. So at the end, the results of our project will be, I think, will be stored in the appropriate way. And so we are meeting and discussing about the use of this fair, standardized, so usable again by everybody. I think in this field is particularly important to do that, because so far there has been very little, let's say, interchange between the computational groups. But since, like for experimentalists, by the way, is very, these calculations are very heavy, like doing an experiment. Actually, it's very similar. To be able to put together and to be able to compare, to to put together in unique database all the results that we get in a way that everybody can use and can reuse again, use again. So I think it will be very important.
Okay, so thank you very much. Is there any additional question from the audience? If not, I really thank you very much, Rita, because also to take all your weekend to prepare this very, very useful and nice presentation. So thank you again. And let me thank all the speakers today that I guess there was a very important, all very important and very nice presentations, hopefully very useful for the future in this field. So we will meet tomorrow here again at 9, where we have